Hello everyone, this is a solution to RMO 2025 P3. It's a geometry problem, so I've already drawn a bit of the diagram. So let's see what's going on. Omega and gamma are circles centered at O1 and O2 respectively. So this is omega, this is gamma, and they intersect at A and B. Suppose O1 is outside gamma, okay, fine, and O2 is outside omega. Let L be not passing through A and B that intersects it's supposed to be intersects, but yeah, it intersects omega at P and R and gamma at Q and S, so that P, Q, R, S lie on the line in this order. This is L, and O1B lie on one side of L, and O2A lie on the other side. Now we're given that A, P, Q, O1 are concyclic, and B, R, O2, S are concyclic. And we are asked to show that AQ, this length, is equal to BR. Interesting. Okay. So we'll start by noticing that O1, okay, in the circle AP, O1Q, O1 is the arc midpoint of the arc PA. It's the major arc midpoint of PA. And we don't really need the major part because that's, yeah, it's just the arc midpoint. It doesn't matter which one. And yeah, why is this true? This is true because O1A is equal to O1P. So it has to be the midpoint of arc. One of them at least. So these two lengths are equal and O1 is the arc midpoint. Since it's the arc midpoint, this means that the line O1Q, this line, it must be an external angle bisector of PQA. Why is this true? I'll draw another diagram. So here we have a circle and a triangle XYZ. What's happening here is that we have the arc midpoint M, and we know that if this is N, this is the other arc midpoint. We know that XN is the internal angle bisector of angle YXZ, and XM, which is perpendicular to XN, this must be the external angle bisector of angle YXZ. These two are perpendicular and XM is the external angle bisector. So what's happened here is that O1Q is the external angle bisector of the angle AQP, right? And that just means that O1Q is the internal angle bisector of the angle AQR, because, well, yeah, this is theta, this is 180 minus theta, and they're joined on the line. So by the definition of external angle bisector, O1Q is the internal angle bisector of angle AQR. Fine. So we know that these two angles, I'll draw them again, these two angles are equal. And I'll set out a claim right here. We should get AQ is equal to QR. Why is this? We already know that AQ is equal to Q. Sorry, what am I saying? We know that O1Q, it bisects the angle AQR, right? Now what I'll do is, I'll show that O1Q also bisects the angle AO1R. I'll erase all of this first so that it doesn't make too much of a clutter. I'll erase these angles as well. Fine. So what I'm going to show is that AO1R, this angle is also bisected by O1Q. Fine. But why is this true? So for this, we'll do a short angle chase. Notice that angle AO1 cube is equal to, since APO1Q are concyclic, this is going to be equal to angle APQ, and APQ is going to be equal to angle APR, since PQ and R are collinear. So of course angle APQ is going to be equal to angle APR. So what I've just shown is AO1Q is equal to angle APR. Now note that angle APR, all of the points on APR, they lie on the circle omega. So APR is going to be equal to angle A1R by 2. But this is exactly what we wanted, because we now have angle A1Q is half of the angle A1R. But that means that O1Q bisects the angle A1R. So that's great. So the configuration we have now, it looks like this. We have the points A, O1, Q somewhere over here, and R over here. And what we have is this line O1Q, it bisects AQR, and it also bisects AO1R. Right. And now what we notice is that angle AO1Q is equal to angle RO1Q. Angle AQO1 is equal to angle RQO1. Why is this? This is because angle AQ, if this point is x, then angle AQX is equal to 180 minus AQO1, but AQX is equal to XQR, and XQR is equal to 180 minus RQO1. So since these two angles are equal, these two angles are also equal. So we have these two angle equalities, but we also have that O1Q is equal to O1Q. What does this mean? These three conditions together tell me that triangles AO1Q and triangles RO1Q are congruent, because all the angles of the triangles are equal, because these two are equal and they have a common side. So these two triangles are congruent, which means that AQ is equal to RQ. In a similar fashion, since the problem is completely symmetric, right, we can get that length BR is going to be equal to length RQ by the same logic. So in the end, what we obtained is that AQ is equal to QR, and similarly by symmetry we can say that BR is also equal to QR, because BR is just the analog of AQ but taken in terms of this B thing. So we obtain that AQ is equal to BR. This is exactly what the problem wanted us to show.